Hello everyone, Mr. Fawcett here, and today we're going to talk about the relationship between differentiability and continuity. In our first unit, we talked about what it meant for a function to be continuous at a certain point, and we had a three-part definition for that. Today we're going to look at what it means for a function to be differentiable at a certain point. So we're going to start off by looking at a bunch of different examples of graphs and thinking about whether we can draw a tangent line at point A. So again, this is leading us into differentiability because the derivative of a function at a certain point is just the slope of that tangent line at that point. So if we can draw a tangent line and find the slope, we would know what the derivative of the function was. If we couldn't draw the tangent line, then we would not be able to figure out what the derivative of the function was, or we would be able to say that it doesn't exist. So let's read the directions, then you're going to pause the video, try this on your own, and then come back and engage in the discussion we have about these different graph examples. So it says, try to draw tangent lines at the given points on each graph. Think about what the slopes of the tangent lines would be if you can draw them. If not, be prepared to explain why you couldn't draw a tangent line. All right, so pause the video, see if you can draw tangent lines at point A. If you can, think about what the slopes would be. If you can't, think about why it's not possible to draw a tangent line. Okay, so for the one in the top right, we can call that number 1. Can we draw a tangent line at point A? Now, initially you may have thought, well, sure, right? Tangent line is just going to look like this. But it's not clear that that would be what the tangent line would look like. Why couldn't I draw the tangent line like this? That still touches the function at point A. Or what about drawing the tangent line like this? So while it may seem like we are able to draw a tangent line here, we're actually not. And this is because the secant line is not approaching the same slope from both sides. So let me kind of show you what I mean there. As I approach, let's say my secant line, we're going to approach from the right-hand side first. As I move, right, if my 2 points are there, my secant line looks like this. And as I move this point closer and closer to where I want to put my tangent line, the slope stays the same, right? Because it's a linear function from 3 to infinity, so the slope is not going to change. The problem is, if I try to draw my tangent line, or try to draw my secant line approaching from the left, well, my slope is always going to be negative. And that's not going to change as I move this point closer and closer to part A. So the one-sided limits of the slope of the secant line as we approach x equals 3 are not the same. One of them is always positive, one of them is always negative, so we don't have an answer to that limit, right? And if the answer to that limit would be the slope of the tangent line. So we don't have an answer to that limit, which means we're not able to draw a tangent line here at point A. Okay, let's look at number 2. Looks like we can draw a tangent line here. And you'll notice, as we look at the 2 secant lines, right? So if I have a secant line coming in from the left-hand side, I can draw a secant line coming in from the right-hand side. Those are going to approach the slope of the tangent line, the blue line that I drew, right? They're going to approach the same slope from either the right or the left. So for number 2, we are able to draw a tangent line, and it would look like what we have in blue. Okay, let's look down at numbers 3 and 4. Okay, let's start with the bottom left, number 3. Okay, so we have a smooth function here, except it's not defined at point A. But right away we may be able to see, okay, I've seen this type of graph before, and I've known that we have a horizontal tangent line here because we have a relative max. The problem is the function is not defined at point A. And if we think back to the definition of a tangent line, one of the things that has to be true about a tangent line is that it has to intersect the function at exactly one point. If I'm trying to draw the tangent line at point A, well, there's no place for the tangent line to intersect the function because the function isn't defined at point A. So if the tangent line can't intersect the function at point A, we actually can't draw a tangent line at point A. So 3, we are unable to draw a tangent line to that function at point A. If we come over here and look at number 4, this is a step function, not a function that we commonly work with in any of our math classes in high school. But let's think about, could we draw a tangent line here at A? Well, as we look at the slope of the secant line as we approach from the right, we would get something that looks like this. So we would get a horizontal secant line. The problem is as we approach from the left, so if I have to pick a point on the function to the left of point A, my secant line is not approaching the same thing from the left as it is from the right. In fact, the secant line is approaching a vertical line as we approach from the left, right? Because as I take a point closer and closer to point A from the left, my secant line is going to look more and more vertical, where my secant line as I approach from the right is going to stay horizontal. So again, the limits of the slopes of the secant lines are not the same as we approach from the left and the right, so we are unable to have a tangent line at point A. Okay, let's see if we have, I think there's 2 more on the next page that I have for us. Yep. Okay, let's look at the one on the left again first. Call that 5. So here we have a linear function, and the nice thing about linear functions is that the tangent lines and the secant lines are always the same, right? As I approach point A with a secant line from the right, that slope is going to be the same as I approach point A with a secant line from the left. And it just turns out that, again, the tangent line at point A is the same as any secant line that you could draw for this graph. So we are able to draw a tangent line to the graph for number 5. It's just going to look exactly like the graph itself. It's going to be the same line. And let's head over to number 6. So can I draw a tangent line at point A? It looks like I can. However, again, the derivative is the slope of the tangent line. So we have a vertical tangent line here, which means our slope is undefined, right? The slope of a vertical line is undefined, which means our derivative here would be undefined. So we wouldn't have a value for a derivative here. So even though we can draw a vertical tangent line, the slope of that tangent line is undefined, which means the derivative would be undefined, which means we don't actually have a derivative here. Okay, let's discuss. We've had a couple of different examples. Some we were able to draw tangent lines for, some we were not able to draw tangent lines for. We should all be able to answer question number 1, though, the relationship between a derivative and a tangent line. So pause the video, take 30 seconds, write down what that relationship is. So I just put the answer up there for us. The derivative is the slope of the tangent line at any given point on the graph. So we already answered number 2. We went through this piece by piece. Which functions would you say the derivative does not exist at point A? So if we just go back up and quickly look again, So for number 1, right, we were not able to draw a tangent line, so we would not have a derivative. The derivative would not exist. So this would be no. For number 2, we were able to draw a tangent line, and the slope was going to be some sort of negative number, so the derivative would exist. For number 3 is a no, right? Because we were unable to draw the tangent line because the function was not defined at point A. So we could not draw a tangent line, which means the derivative would not exist. For number 4, we were not able to draw a tangent line, again, because the secant lines, as we took the limits of their slopes, they were not approaching the same slope from both sides, so we did not have a tangent line, which means we would not have a derivative either. And if we look at our last two, number 5, we were good, right? We said the tangent line was the same as the original function, so our derivative would just be the slope of the function. And number 6, while we could draw a tangent line, the slope of the tangent line was undefined, which means our derivative would be undefined. So we would not have a value for the derivative at number 6. Okay, let's talk about some of the differences that we saw between the graphs that we could draw tangent lines and have derivatives and the ones that we were not unable to draw tangent lines, or the tangent line slope was undefined. So it says, let's brainstorm what had to be true for the tangent lines, i.e. the derivatives. And again, this should be, the derivative is the slope of the tangent line, so let's just keep that clear, to exist in the specific functions above. We will also write down anything we notice about the points where certain functions were not differentiable. So again, take a second to fill in some characteristics for each side of this chart, and then compare your answers to what I put down. All right, so some of the similarities, the functions that were differentiable, and differentiable just means that you were able to take the derivative. Being able to take the derivative means that you're able to draw a tangent line that has a real number slope. So some of the functions that were differentiable, well, all of the functions that were differentiable, they were all continuous at that point A. And they were all smooth curves, so they didn't have hard corners. An example of a hard corner would just be something like this, right? This would be a hard corner. Okay, and we talked about how we were unable to draw a tangent line when we had a hard corner like that. Some of the characteristics about functions that were not differentiable at A, some of the functions were not all continuous. There were some jump discontinuities. There were some removable discontinuities. Some of the functions had hard corners. And one of the functions, we were able to draw the tangent line, but it was a vertical tangent, which means the slope was undefined. It was not a real number. So the function would not be differentiable at that point. The derivative would not exist. All right, let's move on. So now we're starting to sum up what must be true for a function to be differentiable, or for the derivative to exist for a function at a given point. Well, the first thing is the function must be continuous at that point. Next thing is the derivatives from both the left and right sides must be equal, right? So remember we talked about the limit, the one-sided limits of the slopes of the secant lines as they approach that point that we're trying to draw the tangent line at. Those one-sided limits have to be equal. The slopes have to be approaching the same value. They both have to be approaching the same tangent line. So we can write this in two ways. One, using one of our definitions of the derivative. So again, we're just talking about the slope from the limit from the negative side of the derivative being equal to the limit from the positive side of the derivative. But this is generally how we will write this moving forward. Okay, I think it's a little bit easier to understand. We're just using our f prime of x as our notation for the derivative rather than our quotient up top. So as we come down here, it says you can also think of this as meaning that the tangent lines to the graph on the left and right should approach the same tangent line at x equals c. And looking at one of our last couple things for today, I believe there's a couple more things. We're going to squeeze this all into one video, maybe a little bit longer, but that's okay. So note that the criteria for a limit existing is not the same for a derivative existing. Let's take a look at the graph below. And this looks like one of our graphs from up above that we started out with today. So it says, can we take the limit of the function as it approaches a? Explain your answer. So again, pause the video, yes or no, and then explain. Then also answer number 2, is the function differentiable at point A? We've already answered this question, but again, maybe try to explain it again in your own words. Okay, so we are able to take the limit because the function is approaching the same value from both the left and the right-hand sides, which means the two one-sided limits are equal, which makes the actual limit equal. Remember, it doesn't matter that the function's not defined or continuous at that point, because it just matters what the function is approaching, not what the function's value is, whether it does have a value or whether it's not defined at all. Is a function differentiable? That's a different question. So based on our definition above, we can say no. A function must be continuous at a point for it to be differentiable at that point. And because this function is not defined at A, it has a removable discontinuity, it is not going to be continuous at A. Okay, let's look at the next page. Thus, we can say a function must be continuous if it is to be differentiable. However, it's possible for a function to be continuous but not differentiable. And I may encourage you to pause the video, try to draw two different functions that are both continuous but they're not differentiable. So you're not able to draw a tangent line at a point. So two examples would just be something like this, where we have a hard corner. It would not be differentiable at point A. And another example would be something where we have a vertical tangent line. All right, so it would not be differentiable at point A. The functions may be differentiable at other points, just not at these two specific ones. So let's sum this all up. Differentiability implies continuity. So if f, which is a function, is differentiable at x equals c, then f must be continuous at x equals c, right? Because we said if a function's not continuous, it cannot be differentiable. So at the very minimum, if we know that the function is differentiable, then we know that it has to be continuous, because being continuous is one of the initial conditions. Now we have to be careful here. What this is not saying, this does not mean that if f is continuous, then f is differentiable. And we could say at x equals c, at x equals c. So this would be the converse of this theorem up here. But in this case, the converse is false. We've shown in our two examples above, a function can be continuous, but that doesn't necessarily imply that it's differentiable. Okay, differentiability implies continuity, but continuity does not imply differentiability. So just be careful that we don't assume that the converse of that statement is true. Okay, it's been a while since we finished one lesson in one video, but we are just at 20 minutes, which is okay. I look forward to seeing you next time when we learn our first quote-unquote trick for figuring out derivative. It's going to make your lives a lot easier moving forward. Until then, this is Mr. Fawcett. Have a great rest of your day.